Hi, I'm Bob. Let's continue our solutions to problems for Chapter 9. More on specification and data issues. In the textbook Introductory Econometrics, a modern approach, the 7th edition, by Professor Jeffrey Woodridge. For problem 5, the sample selection is likely to be based on the outcome variable, the number of campus crimes. The schools with a higher number tend not to report their campus crimes. So it is an endogenous sample selection. We cannot view it as an exogenous sample selection. We write the equation containing a composite error term, mu I, which equals Ci plus Di times Xi. The requirement for consistency of OLS is the covariance between Xi and mu I is 0. Because mu I is a composite error, we can write the covariance into two terms. The second term can be written out and then simplified. If the covariance between Di and Xi is 0, and the covariance between Di and Xi squared is 0, the second term is 0. If the covariance between Ci and Xi is 0, the first term is 0. So the consistency requirement is satisfied. In other words, if Ci is uncorrelated with Xi, and Di is uncorrelated with Xi and Xi squared, the OLS estimates are consistent. Since AI is Ci plus a constant, and Bi is Di plus a constant, it is equivalent to say that if AI is uncorrelated with Xi and Bi is uncorrelated with Xi and Xi squared, the OLS estimates are consistent. Let's find answers to problem 7. We want to estimate the model where X star is the actual variable. We observed Z equals X star plus E, where E is the measurement error. Now we have M measures for each X star. Let W denotes the average of the M measures. We regress Y on W and an intercept. For the OLS low estimator, beta 1 bar, its probability limit is the true parameter beta 1 plus the ratio of the covariance and the variance. This is the asymptotic OLS inconsistency formula. Next, we derive the variance of W as sigma X star squared plus 1 over M times sigma E squared. Then we simplify the covariance term. Under the zero conditional mean assumption and the classical errors in variables assumption, we can express the covariance term as minus beta 1 times 1 over M times sigma E squared. With all the elements in hand, we can obtain the expression of the probability limit of beta 1 bar. For part 2, we compare the probability limits of the two estimators. When only a single measure is available for each X star, the inconsistency formula for beta 1 hat is as follows in the textbook. We can show that the beta 1 bar is closer to the true parameter beta 1 than the beta 1 hat. The attenuation bias is less severe in the beta 1 bar. In other words, having multiple measures for each individual helps alleviate the attenuation bias. As M grows, the bias becomes smaller. Thank you very much for solving the problems with me. See you soon. Thank you for watching this video and subscribing to my YouTube channel. See you next time.